So last time we were talking about the subtomogram averaging pipeline tutorial. We had gotten through the step of extracting particles last time. So down here, particle extraction. Now, the way we had gone through the tutorial last time, we'd used the deep learning based particle picker, and there's an alternative strategy that you can use here where you box out particles using the reference based particle picker. Which involves generating an initial model first, and then you generate the initial model, and then use the initial model as a reference for picking. So if you did not do that, if you do what we did last time, and you pick particles using the deep learning based picker, then you will still need to go through this initial model generation process to generate a starting model to use later on. This is an automated process. There's an older version and a newer version. I suggest using the new one. They're both automated. They both work very nicely, but the new one works a little bit better. So you just run this E2SPT SGD new. It should be available in the GUI if you're using a current version, which you hopefully all are. So if we look at subtomogram averaging, there's the new initial model generator here. Typically the data is shrunk substantially while you're running this, just to make it run faster, because you don't really need a very good result for the initial model. It just needs to look kind of vaguely like the correct structure. The new initial model generator can actually generate multiple initial models. So you can tell it to generate several different classes, and it will simultaneously try and split the data up into several groups. So if you think you have some heterogeneity in your data set, you could actually try and target addressing some of that heterogeneity immediately in this first step if you want to. You don't need to. You can address it later in the ways that we'll be talking about next week as well. Anyway, so you fill in the parameters here, do the run, and you should wind up with a folder called SPT-SGD00. There will be a variety of files in here. This includes the aligned particles, although this will only be the particles that it elected to use in sort of the final map. There will be aligned 2D particles. Then it will output all of the different maps that it generated in the different attempts that it made, and then finally the one that it thinks is the correct answer. So this is really the output file from that run. So if we double click on, yep.
Can you remind me? I know we talked about this potentially in the file type lecture probably a few months back, but the .list files for the all particles, are those just particle coordinates, I assume, or
an LST file is a text file which is pretending to be an image file.
okay. Is it referencing? Because
It
I know you can also,
references a particle in another file, but it
gotcha.
may optionally contain extra metadata. So we can take a look at one of those. Most of the time they live in sets, but in some of the new strategies that we're using now, we actually have these files appearing in some of the refinement folders as well. So we look at, for example, the 3D file, you'll see that it's got a particle number, it's got a file name, and then at the end here, it'll have some additional metadata, which is present. So what sort of score the particle had when it was building the model, and the 3D orientation of the particle. It's not really very useful in this particular program because it's only saving the few particles that it used stochastically in the process, but in some of the other processes, those files are critical.
Gotcha. Thank you.
Yep. So if we take a look at this output CLS0, you can see, yeah, it looks somewhat like a ribosome. You can see the hole there in the middle between the small and large subunits. And it just sort of has a generally ribosomish sort of shape. So that's good enough to start our refinements from. So you did need to run that process, even if you use the deep learning particle picker. You still needed to do this because we'll need that as an initial model for our actual 3D refinement run. Now you'll notice I have 3 SPT number folders here. Each of those folders represents a run of the new 3D refinement process here. So I ran it 3 different times, 3 different ways with slightly different parameters and stuff, so we can kind of take a look. If we take a look at the tutorial, we are now down at the new integrated refinement program. There is still some information here about the old refinement programs, the old refinement process. This old, what it's calling old here, is not the really old stuff that was done by Jesus a decade ago, where we were really just taking 3D particles and aligning them to each other and averaging them together, and we didn't really have good CTF correction running and that sort of thing. This is the first generation of Muon's programs, which still handled things pretty much the same way. The first stage in the old pipeline was to align the 3D particles to each other, average them together, and then you take those results and then you propagate those into a subtilt refinement, which was based on the individual per particle tilts, tilt images. That approach has changed now in this new program. So the new integrated refinement program does not separate out the 3D and the 2D into separate steps. And unlike the old approach, the 3D particles are never actually used at all. So when you run the new integrated refinement program, one of the things you specify is iterations. And this iteration allows you to specify what type of alignment task or a refinement task to do in each sequential iteration. So this specifies that you want to run 3 iterations. This specifies that you want to run 5 iterations. The P iterations are 3D alignment iterations. You always have to start with at least one P iteration to get the 3D orientation of the particle approximately adjusted. Now, I just said that we weren't using the 3D particles, and that's true. This is the 3D alignment of all of the subtilts held together in the correct relative orientation to one another. So when you do 3D alignment using subtomogram averaging, true 3D alignment, you have to deal with the missing wedge, and you have to deal with the gaps between the slices and that sort of thing. So this new approach just throws all that concept out the window, and it basically says, I just have a set of 2D particles, and I know that those 2D particles have a known geometric relationship to one another. And then when I rotate them around and look for the best orientation for them, I do it in the context where they all have to rotate and translate together. But the energy function that you compute is done just on the individual tilts. So just like you had 50 single particle images, it's just that you have 50 single particle images with some constrained geometry. Okay, so these P iterations give you the 3D orientation of the individual particles in the tomogram, but they do it by working with the 2D data. The T iteration, generally you start with, typically I do 2 P iterations. Sometimes 3 can be useful. It just depends on sort of how good your initial model is and how quickly it kind of converges to the right overall shape. The T iterations are what used to be called subtilt alignment, and these allow the individual subtilt images to be translationally aligned to the reference. This is the key step in achieving high resolution in subtomogram averaging. This is the one thing that all of the different packages that do high resolution subtomogram averaging now, this is sort of the one key thing that allowed us to move beyond sort of 15 angstrom resolution and get decent resolutions in our results, was doing this so-called subtilt alignment. Now this is a translational alignment only. There is another option, R, which allows you to do a rotational alignment. That's just, when it says rotational, we're not talking about a 3D rotational alignment. We're just talking about an in-plane alignment. So it allows each particle to rotate very slightly in plane to try and optimize that. Now, in most cases, pretty much all cases, this does very little that's useful, and it takes a really long time to run because of the slowness of doing the corresponding rotations. T is quite fast. R is pretty slow, and I've rarely seen it make a measurable improvement in the structures. It's available, and it's it's worth a try if you're really trying to push things. D is for defocus. So D iterations allow you to fine tune the per particle per tilt defocus values. Again, in most cases, this doesn't produce very much of an improvement. But if for some reason the defocus values that you have for the particles are off a bit, because for some reason the 3D geometry that it got for the defocuses, maybe this will make a little bit of improvement. Anyway, you can do it. If you're going to do a D iteration, usually you'd want to follow that up with another T iteration at least to try and fine tune things a little bit. You can do PPT and then follow that with another P iteration if you like. Assuming if some of the tilts were just sort of really poorly aligned, once you get the 2D alignment of those tilts a little bit better, then maybe you'll be able to get a better overall 3D alignment as well. So there can be some reason to do, say, a PPT, then another P, and then another T, something along those lines. Anyway, so you need to sort of specify which iterations you want it to run. In the example I'm going to show you, I just ran one big run with I don't know, 7 or 8 iterations all together in one run. So starting from that really low resolution starting model we started from, I just did one run and got the final answer. But you can split it up into sort of sub runs. You can run a few iterations, and you can take the results from that. You can run another refinement from there. Let's see. The top hat option is just like in single particle analysis. This specifies how it will sort of do the final filter and the resolution estimate on the final maps. You can say top hat equals global, in which case it will compute the FSC between the even and the odd halves, and it'll find the 0.143 threshold value, and then it'll do a top hat filter at that point. So the map will be uniformly filtered. If you say local, then it will compute a local resolution across the entire map, and then it will locally filter each part of the map corresponding to that local resolution that it determined. Both are acceptable things to do. One, if you have some parts of the structure that are, say, moving a lot, those portions of the structure may appear, if you do global top hat, those portions of the structure may look kind of noisy stuff because they're not really very well resolved, and it may overfilter some other parts of the structure which were more self-consistent. So if you do top hat equals local, then it gives you the opportunity to get the best possible resolution in sort of each local region. But sometimes it can still overfilter certain parts of the structure and that sort of thing, depending on masking problems and that sort of thing. So yeah, this is something that you can play with. Again, you'll need to specify the parallelism options the same way that we were specifying in the single particle analysis. And that's really about it. In this iteration below, you can say use the gold continue option. If you don't use gold continue and you start from a previous refinement, then it will redo the phase randomization process and the even and the odd halves. So it'll take longer for the refinement to converge a bit. If you've already gone through that process of sort of doing the gold standard alignment once, you don't really have to repeat it again here. So this will make it take fewer iterations to converge, but even without this, you should still get to the right answer. Okay, so this is the run that we're going to do, or that I did next. If we look in my folder here, you can see these are the 3 runs that I did. If we look at this JSON file right here, hit info, and we can look at CMD, which is the command line that I actually ran in this alignment folder. So you can see I ran. You can also use numbers after the letter abbreviations for the types of refinements if you want as a shortcut. So this is equivalent to PP, and this is the equivalent of TT. So you can see I did 2 iterations of the 3D, then 2 iterations of 2D, then another 3D, and then another 2D. Then I did a rotational iteration, and then I did a focus iteration. I didn't follow that up by another T, which I probably should have, but anyway. And I used, let's see, I ran on 32 threads. That 16 is actually superfluous. It doesn't actually do anything. Specifying the M3D thread option is actually a good idea pretty much all the time. When it does the 3D reconstruction process, that uses threads to do it, which requires less memory on the machine. This again, that 16 shouldn't have been there. It didn't hurt anything, but it didn't do anything useful. And I used the top hat equals local. And I told it to keep 95% of the particles. All right, so let's take a look at what we got. So if we look in this folder, SPT00, there's a bunch of files in here. The 3D files are the final structures that came out. We have the FSC files, which are just like the single particle analysis files. You've got a unmasked version, a masked version, and a tightly masked version. Then we also have the LST files, which correspond to all the alignment parameters per particle, per tilt per particle in some cases. The Ali particles 2D files contain the 2D alignment parameters for the in-plane operations, and the 3D Ali particles file has the overall 3D rotational translational alignment for the particles as a whole. So this contains references to the 3D particles if present. So you can see there were 2,385 3D particles and 139,000 2D subtilt images. Normally you're not going to really look at these. You can if you like, but they really are just references to the particles themselves. Okay.
Steve, one question. This is a 3D alignment, but the 2D alignment parameter is generating based on the 3D alignment, right? So all particles 2D is generated.
So you'll note that the 3D files only exist for the iterations where I told it to do 3D alignment. So the first two iterations were 3D, then the next one was and then there were 2D, then there was 3D again. So the Ali particles 2D exists for all of the iterations. So there are 2D alignment parameters present all the time. The 3D parameter is only present when it's doing a 3D alignment.
So then the first two iteration of 2D is that was generated based on 3D alignment.
Yeah, these should basically just be neutral. Yep.
Okay.
Shouldn't really be any alignments there. I mean, it might be previous alignments or something like that that got inherited. Okay. If you tell it to do the local top hat filter, then you'll also get these FSC vol files. These contain the per voxel FSC values. Basically contains a local resolution plot. Often these will be downsampled, although in this case it's actually actually no, that's not true anymore. The new routine for doing the top hat equals local actually does generates them in full sample. Okay, so let's first take a look at the FSC curves to see how it seemed to work. So we'll look at the mask tight version here. All right, so what do we have here? So the first iteration should be at sort of roughly whatever the resolution I told it to do the phase randomization at was. So, this was at something like 25, 26 angstrom resolution. And you can see immediately the 3D refinement already got us down to about 14 angstrom resolution. Then we did an iteration of the translational 2D alignment, and that got us to 11. Then another iteration of the 3D alignment, and then that got us to 9. And then another iteration. So then, hang on, let's take a look at the options again. I don't even remember what they were. Okay, so we had 3D, 3D, 2D, 2D. There we go. 3D. So you can see we did get some improvement out of the 3D alignment after the 2D alignment. Then another 2D alignment. So after doing the 3D alignment, after the 2D alignment, doing the 2D alignment again made another significant jump, and that took us to about 7 angstrom resolution, 6.8. And then the rotational alignment got us a little bit more, so 6.8 to 6.6, and then the defocus adjustment got us maybe a tiny bit more, but not really very much. So the rotation did actually do a little bit here, but not a tremendous. Obviously, the difference between here and here is substantial. The difference between here and here is substantial. This difference, not so much. And this difference, well, I mean, I guess if you really push things, you might be able to make something out of that, but that's not, that's not really real. I probably should have done another round of translational alignment after doing the defocus alignment, because I probably get slightly better defocuses out, and that might push this up just a little bit more. But in general, it looks like we've achieved somewhere around 6.5, 6.6 angstrom resolution. Actually 0.143, so 6.7 angstrom resolution. So that's not too bad. We just did this one run. If we take a look at the files here, you can actually get an idea of how long each iteration took to run. Again, this was running on 32 cores. So the 3D alignment here took about an hour and a half, something like that, hour and 20 minutes. Actually 2 hours. I'm doing math very well in my head right now. And then when we got down to the translational alignment, so that would have been between, say, 3 and 4 here. That was not too much different in time, but an hour and 45 minutes, something like that. The rotational alignment took quite a lot of time, so that would have been the 6 a.m. to 6 a.m. till 1 a.m. the next day. So that rotational alignment step just took a tremendous amount of time. And then the focus alignment, that didn't take too long. That took a couple of hours.
Steve, can I ask one more question? So it's easier to understanding from 3D alignment and changing to 2D substitute. But when you switch back to the 3D, are you using any of the orientations generated by 2D alignment and reconstructing into 3D particles for each one? And
yeah,
yes,
it's always using both. So the 2D alignment parameters are in plane repositioning, and the 3D alignment parameters are full 3D orientation information, which again is constrained to be self-consistent among all the particles. So the 2D alignment parameters are sort of adjustments to where the center of each particle is within its subtilt series.
2D alignment also going to update any of the orientations in 3D? Or your 2D
it doesn't impact the 3D orientations directly. But it impacts where the particle is translationally in the subtilt series. If you have a subtilt series, which you've done in a you've done your tomogram alignment, and you pull out a subtilt series, but say one of the tilts in the subtilt series is shifted by 10 pixels to the left or something like that, because the alignment was done on the whole tomogram and it's not perfect. So near the edge of the tomogram, maybe a little bit less well aligned or something. So if one of the subtilts is, say, off by 10 pixels, when you do the 3D alignment, that's not going to get fixed. When you do the 2D alignment, then that'll get adjusted so its center is in the right position. And then if you go back into a 3D alignment again, it will use that adjusted center position as part of the self-consistent 3D rotations and stuff.
So is it possible we could know that how much of the particle orientation been changed during like this is kind of like doing like iteration by iteration. You could still doing 3D and 2D alignment for more iterations. How could we tell this is going to be approaching to the converged state? You don't need to continue the refinement.
Well, usually you'd look at the FSC curve, and if the FSC curve stops getting better, then you assume that you've achieved convergence. If you like, you could actually look in those LST files and pull out the alignment parameters and see if they're changing much anymore. But that's it's not always a great way of judging. I mean, if you look at single particle analysis, you find that even once you've converged, individual particles may still be shifting around in their orientations and stuff like that. So convergence is sort of pseudo convergence, not true convergence. But yeah, you probably could pull some information out of these Ali particles 2D and 3D files, which would show you whether things were still changing or not.
Oh, okay, I see.
That's not something we do routinely right now, but it's information that is there if you wanted to use it. Okay, so let's take a look at 3D volumes now. I'll just go ahead and open these up sequentially, and we can look at them, at the evolution of them. All right, so that's all 8 of them loaded together. If I open the control panel, we have the slider, which allows us to look at them sequentially. So that was what we got after 1 round of 3D alignment. And you can see it looks pretty much like our initial model, although it's got a little bit more detail than the initial model had. We can actually see some features inside the channel there, and the surface has a little bit more feature, but it's yeah, not all that great. After one more round of 3D alignment, now we have something which looks more ribosome-like. We've got a lot more of the internal features of the ribosome itself, but still, this is something like 15 angstrom resolution. It's not tremendously good structure. Now, after translational 1 round, translational 2nd round, you can see things have gotten a little bit better. Not visually a whole lot better necessarily. I'll note that the color on the surface is a representation of the local resolution. If we look at the ISO surface here, you can see that the coloration ranges from red to green to blue. So the blue colored colored features would correspond to a resolution of something like 6 angstroms, and anything red colored would correspond to a resolution of like 1,000 angstroms or something like that. Anyway, so there's a color gradient there. Anyway, so let's see now what happens if we do after one more round. We switch back to 3D refinement again. And now we're beginning to get some additional details. I think that was 3D. Yeah. And then we've got our final iterations. Now, so this is our final structure. You can see internally there's quite a lot of detail. You can sort of peek through the middle there. You can see a lot of those detailed structures in the middle. Obviously, it's more self-consistent in the middle than it is on the outer surfaces. If we play with the isosurface threshold a little bit here, so here's a nice RNA helix there, and you say, oh, I don't see any of the detailed grooves or anything like that. If we play with the isosurface threshold a little bit, some of that will become a little bit clearer. And now you can see there's some other RNA helices here, which are reasonably nice looking. That one's particularly nice, right? It's like a nice helix. That one's okay too. Anyway, so this is it. This is the final structure that we achieved. Now, what about the other runs I did? Here's the plot again from this first try that I did. This one. I wasn't selecting. Okay. There we go. CMD. So this one I ran PT, and I did a global top hat filter. And we can see there, 1st round, 2nd round, 3rd round, 4th round. Now, this did get a little bit higher in here. So ostensibly, the structures might look a little bit better. But if we look at sort of the limiting resolution down here, it's about the same. So if we open up the final map that we got here and compare that, Here, let's adjust the threshold so they're about the same. That's 4. What's that to about 4? So you can see they're filtered a little bit differently. So this is a local filter where some of these slightly less consistent external features have been low pass filtered a little bit more. This is the global filter where everything's been filtered the same, irrespective of the local resolution. Now, sometimes when you see a local resolution being lower on the surface, that's an impact of the mask, and the mask has had some influence on the perceived local resolution. So there can be some issues with that sometimes. If we take this one, I can play with the threshold a little bit here too, and we can look the level of detail that we're seeing and say the helices isn't really all that much different here, right? So let's do that one at 8.52, 5. Oop, there, right? So you can see. So which one of those you'd want to use? Yeah, maybe you'd want to use the global one. Maybe you'd want to use the local one. It's sort of a matter of how you choose to look at maps in general and that sort of thing. Anyway, so this is about it. This was the final result of the subtomogram averaging process. Now, it turns out, like pretty much all ribosome data sets, there's a fair bit of heterogeneity present in this data set. There's a small set of bad particles which got included in this data set, and it always gets included in the data set when I do irrespective of how I do the picking. But there's there's not very many particles. And there's there's a ratcheting motion, and we can actually see things like tRNA associating and dissociating and stuff like that. So despite the relatively small size of this data set, it is possible to do some heterogeneity analysis on this data. Now, we could do this using just the new 3D refinement variant that permits multi-model refinement, permits classification. So there's so this is E2SPT refine new. E2SPT refine. So you can see there's a E2SPT refine multi-new, which we can use, and that will allow us to do multi-reference refinement using this new subtomogram averaging pipeline. Otherwise, it's very much like the E2SPT refine new. That's not part of the tutorial, but it's something that that you can certainly do. The other approach that you can use is this new Gaussian mixture model approach, which is the last thing we're going to talk about in this little tutorial series. So any questions about the subtomogram refinement before I sort of move on and say a few words about the Gaussian mixture model stuff? We're not going into that in depth today, but I want to get people sort of seated so they can tackle it. Okay. So again, this is what you should be able to achieve using the subtomogram averaging. As you can tell from this, the resolution is just going to be limited by the quality of the data that you've got. We have done a couple of test cases where we've achieved sort of better than 5 angstrom resolution when the data was really good. This data is pretty good. Very often you'll find when people are collecting their tomography data, they're using way too high total dose. And while you can still make use of the data, if you want to start pushing the resolution at all, that means that you're going to have to strongly restrict which tilts you use when you do the 3D reconstruction. Otherwise, you're going to be using heavily radiation damaged images. Now you'd say, what about dose weighting? Can't I compensate for that with dose weighting? Well, no, not really. When you're doing single particle analysis, you can use dose weighting. So the higher dose particles are only contributing at very low resolution, but the high dose particles in tomography are also the high tilt particles in general data collection strategies, which basically means that the high tilt particles are only contributing at very low resolution, which makes them virtually useless. it might help with the alignments just a little bit or something like that. So, there might be some strategy where making some use of them is still warranted. Generally speaking, though, your strategy, if you're planning to target high resolution subtomogram averaging, should be to use lower total dose in your tilt series data collection, use a higher tilt step to get better quality individual tilt images so you can get better quality alignments. So basically move your tomography data collection into something which is more like a single particle data collection where you're just doing some tilting. So don't use a 1 or 2 degree tilt step. Try and target maybe a 5 degree tilt step or even a 10 degree tilt step if you can get your software to do it. 5 is probably fine. And target a total dose over your tilt series of more like 60 electrons or something like that, and then anticipate that you might throw away some of the higher tilt images and only use, say, plus or minus 30 range or something like that. These are the sorts of things that you have to do if you're going to target high resolution when you're using these techniques. All right. So the Gaussian mixture model stuff. So I've been mentioning that we didn't have a tutorial for the new graphical interface version of this. We now kind of do. So I've written a tutorial now. So this is still the subtomogram averaging tutorial. If we go back to EMAN2.org and look under tutorials, standard tutorials, and there's a tutorial for the Gaussian mixture model GUI tutorial. This link has been there for a while, but there wasn't much in it until recently. It is now complete-ish. It is not good. It is not refined. I have not put in a bunch of details. There are places where there are to-dos and stuff like that when I'm talking about some of the theory and that sort of thing. So you may want to look at the paper. But it is usable at this point, meaning you should be able to follow through step by step. So here's sort of a picture of the overall GUI, indicating sort of where the different steps are in the GUI. Yes, I know it looks fairly complicated. It is kind of complicated. And then it's got instructions step by step. So you should be able to follow the instructions, at least at this point, even if there will still be some sort of remaining mysteries after you've gone through the whole thing. So the goal then would be for everyone to try and go through this tutorial before next Monday. Next Monday will be our last meeting before the Christmas break. It might be our last meeting overall. And then we'll sort of talk through some of the results on this. Now, I put this tutorial together such that it makes use of this subtomogram averaging data that we just looked at. I'm going to show you just a couple of things in this interface really quickly today, even if it won't necessarily make a whole lot of sense until you've done it yourself, just to give you some sort of gotchas and that sort of thing about it. You'll note the warning here. The interface to the GMM is still being refined and developed in various ways. So you will still find things, so some of the things in the photo here actually disagree even with this, even though I only made it last week. Now, they don't disagree very much, just there were some rearrangements down here and that sort of thing. But there's still development going on in this interface, but it's definitely at least usable at this point. Now, the thing I want to show you here, what we're looking at in this middle window here is the so-called latent space. It's a projection of the latent space. So when you do the Gaussian mixture model refinement on your data, it will take each particle and it will try and position it in a low dimensional space, low being typically 4 dimensions or 3 dimensions or 5 dimensions or something like that. It'll try to take each particle and position it as a point in this 4-dimensional space. And that point in the 4-dimensional space represents some configuration of the 3D map. So each particle is now associated with a 3D configuration of the particle itself. So here you can see the ribosome particle. I'm going to turn off the map and model here. Now we've got dynamic model and dynamic map. So let me try and do this. Okay. Now what we're looking at here are the motions of the Gaussian corresponding to looking at different parts of this latent space. Now, you'll notice the reason I'm showing you this is in this particular run, we wound up with this sort of line. What you kind of hope to see from this process looks more like this. You hope to see sort of a distribution of particles in space, or something like this, where there's actually some structure, although it's kind of hard to see the structure here. We'll talk more about this next time too, but where there's some structure present in the distribution of points in space. You can see here that there's higher density here and higher density here and higher density here. If you see lines like this appearing, it usually means that the refinement didn't fully converge. Either that, or that there wasn't sort of sufficient variability well defined in the data set to really well characterize it. So these were just so this is one attempt I made to compute the Gaussian mixture model, and this was another attempt I made with slightly different parameters. If you use the parameters I suggest in the tutorial, you should wind up with a distribution kind of like this. If you wind up with a distribution kind of like this, with these sort of with these sort of lines in it or something like that, you might want to try going back and running it again. Now, I had sort of mixed feelings about using this this tomographic data as the basis for the tutorial. The downside about this tomographic data is there's actually very few data points. Each 3D particle is used as a data point here, rather than a 2D particle like it might be. So if we look at this IP3 receptor data set, this had 400,000 particles in it. So there are 400,000 points represented in the space here, and we can do all sorts of fun things like make contour maps and stuff like that with it. In this data set, we've got like 3,000 particles. So it's barely enough to really sort of subclassify things and characterize the dynamics well and stuff like that. The advantage is that you just processed it, so hopefully you have a good reconstruction of it already, and it was done using EMAN2, and it shows that you can actually do this analysis now on tomographic data, not just single particle data. If you have some other project where you've done an EMAN2 style, old EMAN2 style or new EMAN2 style single particle refinement, you could use that data set with the tutorial instead of this data set. But there's a possibility that you might have to tweak some of the parameters. Now, the tutorial does explain some of the parameters, at least in some detail, and I'm going to continue working on the tutorial over the next week while you're using it. But you know, for the moment, it kind of is what it is. What you'd hope to see then is a distribution sort of like this, and if you move around, you should see rearrangements of the Gaussians in the dynamic model. Later in the tutorial, you'll actually generate subclasses, and that'll produce 3D structures of substates. And you can see here, this 1348 here, the particle numbers that you see here are the subtilt numbers, not the 3D particle numbers. And we look at this small subset right here, that's these particles up here, and these are the bad particles. So you can see it's basically just kind of a blob in space, although it's got a little 3D structure to it if we look in the right orientation. Anyway, so these are actually just bad particles up here. Yeah. Okay. Anyway, I think that's all I wanted to say about the Gaussian mixture model stuff this week. Just kind of beware if you try and run on your own data or something like that, and you see stuff like this. If you can't figure out how to solve the problem, you can always send me an email, and I can try and help you out before next week. Next week we'll kind of talk through all of the different steps in this process. Okay. Any questions about any of that? Okay, so before next week, try and apply, go through this this GMM tutorial on some data set. You can use the ribosome tomography data set that we just did. I would not suggest trying to use something like beta-galactosidase because it's a pretty rigid enzyme and it doesn't really have much flexibility. But if you want to try one of the other like the flexible membrane proteins Muyuan uses in his command line based tutorial, you're welcome to try some of the other data sets that are available out there. All right, I think that's basically it for this session. If there are no other questions, we'll stop.